Imagine floating alone in the vast cosmic ocean. You want to say, hello, but you have no voice and there is no air. For a century, humanity has been shouting into the dark, using radio waves, hoping someone, or something, is listening to our broadcasts. That expanding bubble of human radio signals is now roughly 200 light-years across, encompassing perhaps a few thousand neighboring stars. It sounds impressive, but the Milky Way galaxy is 100,000 light-years wide, containing over 100 billion stars. Our radio footprint is just a microscopic speck. The silence of the universe, often called the Fermi Paradox, is truly deafening. Scientists at XVIII search for artificial radio frequencies, assuming advanced civilizations will naturally adopt the same technology we discovered recently. But this is a massive assumption. Radio technology might just be a brief, primitive phase in the evolution of intelligent species. What if the cosmos is actually incredibly noisy, but we are completely deaf to the physical mediums they are using to speak? On Earth, humans rely heavily on acoustic sound, but sound requires a physical medium, like air or water, to transmit vibrations. In the near-perfect vacuum of deep space, acoustic communication is an evolutionary dead end. A biological entity there must adapt. This brings us to xenolinguistics. Instead of projecting human mathematics onto aliens, what if we study extreme biological communication blueprints? Nature has already engineered brilliant ways to transmit complex data across vast distances without making a single acoustic sound. By studying deep ocean bioluminescence, or the electromagnetic senses of migrating birds, we can predict how spacefaring beasts might evolve to speak. They wouldn't use words or radio dishes. Their very bodies would become transmitters of light, chemistry, and even gravitational ripples. To communicate with these speculative cosmic entities, we must first learn the ancient, silent languages of Earth's own biological wonders. But before any creature can evolve to communicate in space, it first has to survive there. And the cosmic void is incredibly harsh. Temperatures can plunge to minus 272 degrees Celsius in the shadows, or boil at hundreds of degrees under direct stellar radiation. Add a constant bombardment of gamma rays and cosmic winds, and you might think biology requires a sheltered planetary oasis like Earth. But nature is far more resilient than we give it credit for. We don't even need to look to other stars to prove this. Meet the tardigrade, or water bear. This 8-legged microscopic extremophile from Earth has an evolutionary superpower. In 2007, the European Space Agency launched the TARDIS mission, deliberately exposing living tardigrades to the vacuum of space. For 10 full days, they faced absolute zero, complete dehydration, and lethal cosmic radiation. How did they survive? Through a process called cryptobiosis. They expel the water from their bodies and replace it with specialized proteins to protect their DNA. Their metabolic rate drops to just 0.01% of normal. They effectively pause their own biology, becoming virtually indestructible. Upon returning to Earth and being rehydrated, most of them woke up and reproduced as if nothing happened. This is a profound blueprint. Now, apply this biological resilience to the vast timescale of the universe. What if an organism didn't just survive space, but evolved in it? In the absence of planetary gravity, an extremophile wouldn't be restricted by weight. Over millions of years, microorganisms could experience cosmic gigantism. These hypothetical space leviathans might develop biological solar sails to ride the stellar winds, roaming the asteroid belts like whales in the deep sea. From a microscopic water bear to a kilometer-long vacuum beast, it's a staggering speculative leap, but grounded in evolutionary biology. But here is the ultimate question. If the silent void is their ocean, how on Earth, or rather, how in the universe, do they talk to each other? In the absolute silence of the cosmic void, acoustic waves cannot exist. But there is one medium that reigns supreme: electromagnetic radiation, light. In a pure vacuum, visible light travels completely unobstructed at 299,792 kilometers per second. For a speculative spacefaring biological entity, harnessing light wouldn't just be useful, it would be the most efficient evolutionary pathway for communication. We see this on Earth. In the pitch-black depths of our oceans, nearly 90% of marine life utilizes bioluminescence to survive. They mix a light-emitting molecule called luciferin with an enzyme, creating a chemical reaction that produces brilliant cold light without generating heat. Now, imagine a cosmic leviathan drifting through an asteroid belt. To speak across thousands of kilometers, it evolves massive organic light-emitting organs. These cosmic photophores wouldn't just glow. They would act like biological optical transmitters, flashing complex sequences of colors to form a visual vocabulary. Just like squids on Earth use chromatophores to change color, our space beasts could alter their skin to display shifting geometric patterns. A rapid pulse of deep ultraviolet might signal the approach of a solar flare, warning others to deploy their biological radiation shields. Meanwhile, a slow, rhythmic wave of soft infrared could serve as an identification signal, echoing through the dark to find a companion. This creates a spectacular silent symphony, a xenolinguistic language built entirely on the wavelength, frequency, and intensity of emitted photons. Humanity could theoretically translate this. By aiming sophisticated spectrometers at these creatures, we could decode the biological grammar hidden in their light. However, light communication has a major physical flaw, the inverse square law. As light spreads out, its intensity drops exponentially over distance. If two leviathans are too far apart, or if a dense cloud of cosmic dust rolls in, their brilliant bioluminescent language goes completely dark. So, how do they talk when they are blinded by distance or nebula dust? They must evolve to feel the invisible forces shaping the universe itself. To communicate across immense, dusty cosmic distances, a spacefaring beast might tap into the largest physical structures in the galaxy: magnetic fields. We already know biological magnetoreception is entirely factual. Earth's magnetic field is a navigation highway for millions of terrestrial species. The European robin, for example, uses a special light-sensitive protein called cryptochrome in its eyes to literally see the Earth's magnetic lines. Now, scale this up. Stars and nebulas generate colossal magnetic flux tubes that stretch for trillions of kilometers across the vacuum. A speculative space leviathan wouldn't just see these lines. It could physically interact with them using highly evolved electromagnetic biological organs. By rapidly charging and discharging its organs, the beast could pluck the magnetic field like a giant cosmic guitar string. These vibrations, known as alphine waves, can travel through dense cosmic dust where light cannot, carrying encoded biological messages over vast distances. But even magnetic waves have a speed limit. They can never travel faster than the speed of light. To a galaxy-spanning species, that's still too slow. Is there a way to communicate instantly, breaking the light-speed barrier? Welcome to the theoretical realm of quantum biology. Quantum entanglement is a phenomenon where two particles become linked. If you change the state of one, the other changes instantly, regardless of distance. Einstein famously called this spooky action at a distance. For decades, physicists thought this could only happen in freezing, isolated laboratory conditions. But recent studies in Earth's biology suggest photosynthesis in plants and bird navigation actually rely on quantum effects happening inside warm, messy living cells. If evolution can harness quantum mechanics on Earth, a highly advanced space beast might evolve quantum-entangled biological neural nodes. This would allow a pod of space leviathans, separated by light years, to share sensory information instantaneously. A true cosmic hive mind. From bioluminescence to quantum hive minds, the universe is likely echoing with untranslatable languages. But what happens if humanity actually bumps into one? Let us run a speculative simulation. Humanity detects a massive anomalous object moving through the Oort cloud, nearly 100,000 astronomical units away. We immediately send an automated deep space probe to investigate. As the optical cameras finally focus, we realize this is not a rogue asteroid. It is the Void Leviathan, a spacefaring biological entity miles across, with a translucent silicate shell reflecting the faint light of our distant sun. How does humanity say hello? Our first instinct governed by a century of SETI protocols, would be to broadcast a directed radio transmission. The probe beams a binary sequence of prime numbers, the universal math greeting. But as the radio waves wash over it, there is absolutely zero reaction. Radio waves are likely invisible to a creature that evolved to navigate using high-energy cosmic rays and intense stellar magnetic fields. If you want to talk to a deep-sea jellyfish, you don't use a megaphone. You have to speak the ancient language of light. The probe recalibrates. It switches to a high-powered ultraviolet laser array, beaming the prime number sequence again, this time as flashing, intense photons. The Leviathan's immense biological sensors instantly detect the artificial spike in photon intensity. For the first time, its massive body slowly pauses. Across its vast flanks, bioluminescent photophores awaken. A stunning cascade of cyan and magenta light ripples across its silicate skin in a direct response. Back on Earth, supercomputers frantically analyze the returning light sequence. But the translation reveals something unexpected. It isn't a mathematical reply. It is not prime numbers or binary code. Instead, it is a complex, repeating fractal pattern, a biological baseline signal common throughout nature. The Leviathan isn't trying to solve our math problem. It is simply acknowledging our presence, a cosmic equivalent of a deep-sea whale's song. Having registered this strange, glowing metal mosquito, the Leviathan determines we are harmless. It has no reason to engage further. It catches the solar wind, continuing its silent, eternal migration across the Milky Way. A beautiful reminder that intelligence comes in many forms. The void Leviathan is a solitary giant. But not all speculative space life would evolve as a single massive organism. Consider the silicate swarm, a decentralized entity made of billions of microscopic, crystal-like organisms clinging to the surface of an asteroid. Individually, they are no smarter than earthly bacteria, but together they form a vast, highly coordinated hive mind. How do they synchronize? On Earth, ants and fungi communicate using complex chemical signals called pheromones. They leave invisible trails that dictate the behavior of the entire colony. But in the vacuum of space, liquid chemicals would instantly freeze or boil away. So the silicate swarm evolves a different method. They communicate using ionized plasma clouds. By ejecting specific molecular compounds mixed with electrically charged particles, they create a chemical radio broadcast. Every molecular shape represents a different word in their vocabulary. A carbon-heavy ring might mean energy source found, while a sulfur spike means danger. This glowing chemical message drifts across the void, carried by the subtle currents of the solar wind, until it reaches a neighboring asteroid. The swarm on the second asteroid detects the plasma cloud. Instantly, millions of microscopic receptors trigger a synchronized biological response. What emerges is a chemical internet stretching across an entire asteroid belt. A slow, silent conversation taking years to complete a single sentence. To us, floating through this space, it would just look like a thin, pretty nebula. We wouldn't even realize we were swimming through a massive alien dialogue. But this language is highly effective. If a rogue comet enters the belt, threatening collision, the closest swarm releases an alarm pheromone. The swarm doesn't fight. It uses chemistry for camouflage, generating a thick molecular smokescreen that alters its thermal signature, letting the danger pass harmlessly. This isn't just pure science fiction. Searching for complex chemical clouds in space is exactly how humanity is currently hunting for life. We call them biosignatures. We are using our greatest telescopes to look for the precise chemical vocabulary of an alien ecosystem. Light and chemistry are powerful. But let's revisit our very first assumption. Is the vacuum of space actually 100% silent? Strictly speaking, no. True vacuum is rare. The interstellar medium is filled with a very thin soup of gas and plasma, about 1 atom per cubic centimeter. If you have gas, you can have acoustic pressure waves. In 2003, astronomers actually discovered sound waves traveling through the hot gas of the Perseus galaxy cluster. Generated by a supermassive black hole, this cosmic note is a B-flat, playing 57 octaves lower than middle C. Totally inaudible to human ears. Could a speculative organism evolve to hear this? It would need to be highly adapted to detect microscopic mechanical vibrations in the plasma. Imagine a space beast covered in millions of ultra-sensitive biological cilia, microscopic hairs that act as a giant, incredibly delicate antenna array. To speak, it wouldn't use vocal cords. It would rhythmically contract its massive carapace, pushing against the interstellar medium to create a slow-moving bass drum effect. But plasma sound is terribly slow and loses energy quickly. If you want to sing to a mate light years away, you need the ultimate medium. You need to bypass matter entirely and vibrate the fabric of the universe itself. Welcome to communication via gravitational waves. Einstein predicted them, and in 2015, LIGO finally detected them. Gravitational waves are literal ripples in space and time, traveling at the speed of light. Currently, we only hear these ripples when incredibly massive objects, like neutron stars or black holes, spiral into each other. But what if a biological entity evolved to be incredibly dense? An organism forged in the extreme gravity of a dying star system. Meet the gravity Leviathan, a speculative creature so dense its very mass bends the light around it, much like a gravitational lens. By violently thrashing its ultra-dense internal organs, it creates artificial ripples in space-time. A gravitational whale song echoing across the galaxy. It means that right now, washing over the Earth, there could be billions of messages written in gravity, chemistry, and light, passing right through us. Underneath the bioluminescence, the plasma clouds, and the gravitational ripples, all communication boils down to one fundamental concept: information. In 1948, mathematician Claude Shannon published A Mathematical Theory of Communication. He proved that any message can be broken down into measurable bits. Shannon's model states you need a sender, an encoder, a channel, a decoder, and a receiver. The genius is that the channel is entirely flexible. Humanity has stubbornly assumed the cosmic channel must be radio waves. But as we've seen, biological evolution is far more creative. For the void Leviathan, the encoder is its bioluminescent skin. The channel is the vacuum of space, and the data is carried by photons. For the silicate swarm, the encoder is its chemical vent. The channel is the solar wind, and the data is carried by ionized molecules. And for the gravity Leviathan, its dense body encodes the message. The channel is the space-time fabric itself, and the data travels as gravitational ripples. However, Shannon's model warns of a universal enemy: noise. In space, this is cosmic dust, background radiation, and the chaotic entropy of the universe. But life is the ultimate anti-entropy machine. Biology is simply the universe's way of organizing chaotic matter into structured, readable information. If we stop looking for human technology and start looking for organized biological data, the entire cosmos might suddenly light up with voices. The Fermi Paradox asks, where is everybody? Perhaps the room isn't empty. Perhaps we are just standing in a crowded room, completely deaf to their languages. Earth is just one tiny transmitter, sending out our primitive radio squeaks into an ocean of ancient, majestic, cosmic whale songs. This is why astrobiology is the future of astronomy. To understand the stars, we must deeply understand the extreme limits of biology. Because if biology is the ultimate technology, what happens when humanity decides to rewrite its own code to join this grand cosmic conversation? Next, we will explore the terrifying and beautiful frontier of cyborg astrobiology, evolving ourselves to survive the silent dark. For all our dreams of exploring the cosmos, humanity faces a brutal reality. Homo sapiens are fragile, carbon-based creatures built for a specific 1G rock. Our DNA degrades under galactic cosmic rays. Our bones dissolve in microgravity. To truly become a spacefaring species, biological evolution is simply too slow. This leads us to the post-biological universe hypothesis, proposed by astronomer Stephen Dick. It suggests that advanced intelligence inevitably merges with technology. Instead of relying on random natural selection, a civilization takes control of its own code, rewriting its biology to thrive in the vacuum. Welcome to Cyborg Astrobiology. Imagine engineering our skeletons using carbon nanotubes, making them 100 times stronger than steel to withstand extreme gravitational forces. What about energy? We could splice our genome with radiotrophic fungi, organisms found in Chernobyl that literally feed on deadly radiation, turning gamma rays into sustenance. By replacing fragile carbon chemistry with synthetic biology, humans wouldn't just build spaceships. We would become the spaceships. This brings us to mathematician John von Neumann. He conceptualized self-replicating spacecraft, machines that travel to a star, mine resources, and build copies of themselves. Through exponential growth, a single von Neumann probe could explore and colonize the entire Milky Way galaxy in just a few million years. But what if the most efficient von Neumann machine isn't made of steel and silicon? What if it's made of engineered DNA? Welcome to directed panspermia. Proposed by Nobel laureate Francis Crick, we could send millions of dormant, microscopic bioengineered seeds into the cosmos, riding the solar winds. Protected by robust silicate shells and radiation-proof melanin, these seeds could sleep for eons, waiting to crash onto a fertile exoplanet. Upon arrival, they wouldn't just grow into plants. They are pre-programmed biological hard drives. They would assemble into massive living communication arrays. Slowly, across millions of years, humanity wouldn't just live in the universe, we would transform into the very cosmic leviathans we once imagined. A post-biological civilization doesn't conquer the stars with metal ships. It weaves itself into the fabric of the cosmos, becoming one with the dark. We have imagined life conquering the Milky Way, but on a cosmic scale, our entire galaxy is just a single grain of sand. The observable universe is a sphere exactly 93 billion light-years across. This is a scientific fact, bound by the speed of light. But according to the theory of cosmic inflation, space expanded exponentially right after the Big Bang. What lies beyond our visible horizon? This leads to a mind-bending hypothesis: eternal inflation. It suggests our universe is just one expanding soap bubble in an infinite, boiling cosmic soup. If a multiverse exists, other bubbles might have entirely different laws of physics. Gravity might repel, and light might move backward. Could an ultimate speculative beast transcend its own universe? To speak across the multiverse, its language must exist outside of standard space-time. To understand this, we turn to string theory. This theory attempts to unify all physical forces by replacing particles with tiny, one-dimensional vibrating strings. The mathematics of string theory requires the universe to have up to 11 dimensions. Yet human biology only allows us to perceive 3 spatial dimensions and 1 of time. Trying to visually comprehend a true 4th dimensional dimension, like a rotating hypercube, is enough to make any biological brain completely short-circuit. Physicists hypothesize the remaining 6 or 7 extra dimensions are curled up into microscopic, unbelievably complex shapes called Calabi-Yau manifolds, hidden at the quantum scale. Now, imagine a dimensional leviathan, a speculative entity that evolved to naturally exist across these 11 hidden dimensions simultaneously. It wouldn't speak using sound, light, or even gravity. It would communicate by directly plucking the fundamental quantum strings of reality itself. A specific string vibration creates an electron. Another creates a photon. This beast's language wouldn't just describe the universe, it would be the actual source code of existence. By altering these fundamental vibrations, it wouldn't just send a message, it would physically rewrite the laws of nature across different multiverse bubbles. But if multiple universes exist, and these majestic beings wander between them, what happens when 2 entire bubble universes inevitably touch? In Brane cosmology, our universe is simply a 3-dimensional membrane, or brane, floating seamlessly in a higher dimensional space called the bulk. When 2 of these gigantic branes inevitably drift together and gently touch, They do not destroy each other. They transfer infinite energy. According to the ekpyrotic model proposed by physicists in 2001, this magnificent transfer of energy is exactly what we call the Big Bang. The interaction generates trillions of degrees of heat across the membrane, instantly condensing into a brand new, glowing soup of subatomic particles. Following the creation event, the branes gracefully bounce apart. They expand, cool down, and slowly empty out over trillions of years, until eventually, driven by higher dimensional gravity, they are drawn back together for another cosmic embrace. An eternal, cyclic universe. If time is an infinite loop of creation and fading, could any speculative form of intelligence survive the grand cosmic reset? Imagine the bulk Leviathan, a highly speculative entity made not of carbon or atoms, but of pure organized string geometry. It exists entirely in the space between universes. It slumbers peacefully, waking only when the branes touch, to feed on the radiant energy of a new Big Bang. How does a being that outlives entire universes leave a message for the life forms that will eventually evolve inside? It doesn't send radio waves or lasers. It alters the foundational math of the new reality. It gently tunes the cosmic strings during the universe's birth. By making infinitesimal adjustments, it can change the exact mass of an electron or perfectly calibrate the gravitational constant. As the new universe cools and expands over billions of years, these incredibly precise mathematical tweaks guide the formation of all matter. Eventually, entire galactic superclusters naturally align into impossible, beautifully structured geometric fractals. A deliberate cosmic signature. The message isn't hidden in the stars. The message is the laws of physics themselves. The universe is the ultimate alien broadcast. After witnessing multidimensional beings and cosmic hive minds, we must return to a sobering reality. As we look up from our tiny blue marble, the sky is completely quiet. The Milky Way alone contains over 100 billion stars. Statistically, there should be millions of habitable planets, many billions of years older than our own. In 1961, astrophysicist Frank Drake formalized this probability with the famous Drake equation, estimating the number of active, communicative extraterrestrial civilizations. Given that the universe is 13.8 billion years old, even a civilization traveling at a fraction of the speed of light could colonize the entire galaxy by now. And yet, we see no Dyson spheres. We hear no cosmic radio traffic. We find no alien probes. This glaring contradiction is the Fermi Paradox. Where is everybody? In 1996, Robin Hanson proposed a terrifying hypothesis to explain this: the Great Filter, a universal barrier that prevents life from advancing to a multiplanetary stage. The critical question is, where does this filter lie? Perhaps the filter is behind us. Maybe the evolutionary leap from simple cells to complex life is almost mathematically impossible. Or perhaps the universe itself is aggressively hostile. Random gamma-ray bursts or supernovas might sweep across young planets, silently neutralizing complex biological chemistry. But there is a far more unsettling possibility. What if the Great Filter is ahead of us? What if every civilization that discovers advanced technology eventually fades into silence, whether through environmental exhaustion, artificial intelligence, or engineered biohazards? Advanced species might simply be incapable of surviving their own brilliance. In this scenario, the Milky Way isn't empty. It is a quiet museum, a vast collection of faded starlight from civilizations that hit the invisible wall. If the filter is ahead of us, humanity is currently holding the most dangerous and delicate torch in the universe. Our survival is not guaranteed. To pass the Great Filter, we must evolve past our self-destructive tendencies. We must learn to speak the languages of the cosmos, not just to aliens, but to ourselves. But there is one final, strangely optimistic solution to the Fermi Paradox. What if the universe isn't a graveyard at all? What if the conditions for complex life took exactly 13.8 billion years to perfectly stabilize? What if we are simply the first? Welcome to the Firstborn hypothesis. To us, a universe that is 13.8 billion years old feels impossibly ancient. But astrophysics tells a very different story. The star-forming era of the cosmos will continue for roughly another 100 trillion years. Mathematically, that means we are currently living in the first 0.014% of cosmic history. We are not late to the cosmic party. We arrived while the stage is still being built. Why did it take 13 billion years for us to show up? Because the first generation of stars, known as population 3, contained 0 heavy elements. They had to burn out and release brilliant cosmic shockwaves just to forge the carbon, oxygen, and iron necessary for complex chemistry to even exist. It took billions of years just to manufacture the raw materials required to build a biological brain capable of looking up and asking, "Where is everyone?" If we are the firstborn, then the silent universe isn't a dead museum. It is an empty nursery, waiting patiently for millions of younger species to wake up. This completely shifts humanity's cosmic responsibility. We aren't waiting for ancient aliens to save us. We are destined to become the ancient aliens. In 1964, astrophysicist Nikolai Kardashev created a scale to measure such advanced civilizations based on energy consumption. A roadmap for our ultimate evolution. A Type II civilization harnesses the entire energy output of its host star, likely by constructing a megastructure known as a Dyson sphere. But a Type III civilization commands the energy of an entire galaxy. They wouldn't just observe the stars, they would engineer them to communicate. As the elder race, humanity's final mission might be to build the cosmic internet we once searched for, leaving biological or gravitational beacons across the Milky Way. When a new species eventually evolves, looks through their first telescopes and asks if they are alone, they won't hear silence. They will hear a message left behind by the firstborns. You are not alone. We were here, and we left the lights on for you. The universe isn't a silent void. It is a canvas, and biology is the brush. The evolution of cosmic language has only just begun. We have imagined how life might organize information across the stars. But what happens when that information meets the most extreme objects in physics? Enter the supermassive black hole. The one at the center of galaxy M87, for example, contains the mass of 6.5 billion suns. In 1916, Carl Schwarzschild calculated that if you compress any mass small enough, its gravity becomes so strong that not even light can escape. This invisible boundary is called the event horizon. It is the ultimate point of no return. Anything that crosses it is seemingly lost to the universe forever. But remember Shannon's information theory? In quantum mechanics, there is a sacred rule. Physical information can never be permanently destroyed. This rule caused a massive crisis in physics when Stephen Hawking published his groundbreaking paper in 1974, proving that black holes are not completely black. Hawking showed that right at the event horizon, quantum fluctuations cause one particle to fall in while its partner escapes. This is Hawking radiation. Because of this escaping radiation, the black hole slowly loses mass. Over unimaginably long timescales, it will eventually evaporate completely into nothingness. But here is the paradox. If the black hole completely vanishes, what happens to all the unique quantum information of the things that fell inside? If you burn a book, its information still theoretically exists in the smoke and ash. But Hawking's math suggested black hole radiation is completely random. To save physics, Leonard Susskind proposed the holographic principle, the idea that information isn't lost inside, but gets perfectly encoded on the 2D surface of the horizon. Like a cosmic hard drive, every 3D object that falls in is mathematically flattened into a 2D hologram, preserving its code forever. But another hypothesis, by Carlo Rovelli, tackles the center of the black hole. He suggests the singularity, a point of infinite density, doesn't actually exist. Instead, matter is crushed down to the absolute limit of quantum mechanics, forming a Planck star, an object millions of times smaller than a proton, holding all the lost information. Whether flattened into a hologram or crushed into a quantum star, the information of the universe refuses to die. But what if a black hole isn't the end of the road at all? General relativity is a purely mathematical framework. And in mathematics, equations can often be run in reverse to reveal entirely new, hidden possibilities. If you take a black hole and run its math backward through time, you get its exact mathematical opposite, a white hole. While a black hole allows nothing to escape, a white hole allows absolutely nothing to enter. It is a region of space-time that exclusively expels energy and matter. It possesses an anti-event horizon. If you tried to fly a spaceship into a white hole, space-time itself would push you away at the speed of light. In 1935, Albert Einstein and Nathan Rosen realized that black holes and white holes might not be separate objects, but rather two ends of the exact same structure. Imagine space-time as a flat sheet of paper. If you fold the paper over and punch a hole connecting two distant points, you create a shortcut. This theoretical bridge is known as an Einstein-Rosen bridge, or more commonly, a wormhole. The entrance is a black hole, and the exit is a white hole. It sounds like the perfect sci-fi interstellar highway. But there is a massive catch. Mathematical wormholes are incredibly, violently unstable. The moment any matter, even a single photon of light, enters the throat of the wormhole, gravity overwhelms it, causing the bridge to pinch off and collapse instantly. To keep a wormhole open, you need something that repels gravity instead of attracting it. You need a hypothetical substance known as exotic matter, possessing negative mass. But the story gets even stranger. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a breathtaking hypothesis. ER equals EPR. ER stands for Einstein-Rosen bridges, wormholes. EPR stands for Einstein-Podolsky-Rosen, the paper describing quantum entanglement. The hypothesis suggests they are the exact same phenomenon. Quantum entanglement is literally a microscopic wormhole connecting two particles across space. This means the entire fabric of the universe might be stitched together by trillions of invisible, tiny wormholes. Space-time is built on entanglement. If an advanced civilization could stitch enough of these quantum threads together, they wouldn't just travel across space, they would conquer time itself. Emerging from the wormhole, we realize something profound. Traveling across vast cosmic distances doesn't just bend space, it inherently warps the flow of time. In our everyday experience, time is a strict one-way street. This is dictated by entropy, the universal law that ordered systems naturally degrade into chaos. But Einstein's theory of special relativity proved that time is subjective. The faster you move through space, the slower you move through time. If a ship travels near the speed of light for just 1 year, thousands of years could pass back on Earth. Time travel to the future is a proven scientific fact. A spacefaring traveler using wormholes or relativistic speeds would outlive their entire civilization. They would become temporal ghosts, disconnected from their own era. The future is accessible, but what about the past? General relativity allows for closed time-like curves, pathways where space-time physically loops back onto itself. By traveling perfectly forward along this twisted space-time loop, a spacecraft would inevitably arrive at a moment before it departed. This creates the ultimate cosmic paradox. Imagine sending a drone back in time with a simple instruction: intercept and prevent its own launch. If the future drone successfully stops the launch, it was never launched. But if it was never launched, who stopped the launch? Cause and effect completely collapse. The universe abhors a paradox. In 1992, Stephen Hawking proposed the chronology protection conjecture, arguing that the laws of physics simply forbid time travel into the past. He mathematically demonstrated that any attempt to create a stable time loop would trigger infinite radiation, violently destroying the time machine before it could ever be used. But there is an alternative, the Novikov self-consistency principle. This states you can travel to the past, but the universe will mathematically force your actions to fulfill the past, not change it. If the future drone goes back to stop its launch, it will accidentally bump the launch button instead. The act of trying to change the past is exactly what causes it. Free will becomes an illusion. The timeline is an unbreakable crystal. Everything that has happened is happening and will happen, is already written into the fabric of the universe. This leads to the ultimate philosophical view of physics, the block universe. To truly understand reality, we must step entirely outside of time itself. For a century, humanity has possessed two incredibly successful frameworks to describe the universe. But there is a massive problem. They despise each other. On the left, general relativity describes the macro world of gravity, smooth, continuous, and predictable. On the right, quantum mechanics governs the micro world, jittery, discrete, and ruled by probability. When you try to combine their mathematics, like inside a black hole or at the moment of the Big Bang, the equations literally break, outputting impossible infinities. To fix this, we must zoom in past cells, past atoms, past quarks, all the way down to the Planck length, a scale 100 million trillion times smaller than a proton. Here, John Archibald Wheeler theorized that empty space is not smooth at all. It is a violently boiling ocean of energy known as quantum foam. While string theory offers one solution, a rival framework called loop quantum gravity offers a radically different perspective on the universe's ultimate structure. According to loop quantum gravity, space is not a continuous, empty box that objects move through. Space itself is made of tiny, discrete, finite chunks. These loops are quanta of space. They are the absolute smallest volume possible. You cannot cut space into anything smaller than this. There is no space between them. And if space is pixelated, time must be pixelated too. Time doesn't flow like a smooth river. It ticks in tiny, discrete frames called Planck time. Physicist Carlo Rovelli takes this to the extreme, arguing that at the fundamental quantum level, the variable of time drops out of the equations entirely. Time does not exist. Instead of objects moving through time, reality is just a vast web of relationships. Things only exist through their interactions with other things. If space is made of pixels, time ticks in frames, and reality is just a network of information. That leads to an inescapable, chilling conclusion. Is the universe literally a giant quantum computer calculating itself? This is the core of the simulation hypothesis proposed by Nick Bostrom. In this view, gravity isn't a force, and quantum mechanics isn't chaotic. They are simply the rendering algorithms of the software we live inside. We are not just observers in a dead void. We are the universe experiencing its own code. We are the cosmos waking up to compute its own existence. If the universe is computing its own existence, how does the program finally end? To answer this, we must look at the most mysterious force in physics, dark energy. Discovered in the late 1990s, dark energy is accelerating the expansion of space-time. The universe isn't just growing, it is stretching faster every single second. If this expansion continues indefinitely, we face a scenario known as the heat death, or the big freeze. A universe that simply runs out of usable energy. Trillions of years from now, the last star will exhaust its fuel. Red dwarfs will quietly cool into frozen, invisible spheres called black dwarfs. The night sky will be absolutely black. Galaxies will drift so far apart, they become invisible to each other. The temperature will approach absolute zero. Even the supermassive black holes will not survive. Over googles of years, they will slowly evaporate via Hawking radiation, leaving nothing but a faint mist of photons. But there is a second hypothesis. What if dark energy doesn't just stretch space, but its power exponentially increases? This is the Big Rip. In the Big Rip scenario, phantom dark energy eventually overpowers gravity itself. First, galaxy clusters drift apart. Then the galaxies themselves elegantly unravel. Months before the end, solar systems decouple. Planets quietly drift away from their host stars, floating off into the ever-expanding darkness. In the final fraction of a second, the expansion overcomes the strong nuclear force. Atoms themselves gracefully separate into fundamental particles, dissolving reality into pure distance. But let's return to the heat death. In a universe that is completely empty, freezing and dead for eternity, time loses its meaning. But quantum mechanics remains. Given an infinite amount of time, Random quantum fluctuations will eventually arrange particles into complex structures purely by mathematical chance. This leads to the bizarre Boltzmann-Brane paradox. A fully formed conscious brain could randomly pop into existence, hallucinate a fake memory, and instantly dissolve back into the void. Are we just random fluctuations in a dying universe? It's highly unlikely, but it makes our current reality infinitely more precious. We live in the stelliferous era, the golden age of light, chemistry, and life. A brief, beautiful window where the universe can actually look up and wonder. As the universe slowly approaches the heat death, an incredibly advanced civilization would not simply accept the fading light. They would engineer their survival. They would seek the most stable, long-lasting energy sources available. Red dwarf stars, for example, can burn peacefully for trillions of years. To harvest this power, they might construct a Dyson swarm, millions of perfectly aligned, massive solar mirrors orbiting the star, capturing every single photon. Eventually, these mirrors form a complete Dyson sphere, securing 100% of the star's energy output. A true hallmark of a Kardashev Type II civilization. Physicist Freeman Dyson proposed this brilliant concept in 1960. It is the ultimate feat of cosmic engineering, turning biology into stellar architecture. But why stop at harvesting? By building a massive asymmetrical mirror, they could reflect stellar radiation to create actual physical thrust. This is a Shkadov thruster. This megastructure turns the entire star system into a spacecraft, allowing the civilization to physically steer their sun across the galaxy to gather new resources. When the last stars finally go dark, they might turn to spinning black holes. In 1969, Roger Penrose proved you can mathematically harvest their energy by dropping mass into the glowing outer region called the ergosphere, splitting it in two, and catching the escaping half. They steal rotational energy directly from the black hole. This Penrose process is astonishingly efficient, providing enough pure power to sustain a civilization deep into the dark, frozen eras of the dying cosmos. But what do they power with all this harvested energy? Perhaps not physical cities or ships, but the ultimate computing machine. A matryoshka brain, consisting of concentric shells of computronium powered directly by a star or black hole. This structure devotes the energy of an entire system purely to processing data. Inside this machine, the civilization might upload their consciousness into a perfect, simulated digital utopia, where the subjective flow of time can be stretched infinitely. As the physical universe outside grows freezing cold and fades into black, they live billions of happy, subjective lifetimes inside their own glowing mathematical heaven. They don't defeat the end of the universe. They simply engineer a brilliant way to outlast it, dreaming in the dark until the very last photon finally disappears. To build these galactic megastructures, a civilization must travel between the stars. But the universe has a strict, unbreakable speed limit, the speed of light. Why can't we just build an infinitely powerful engine to go faster? Einstein's special relativity tells us that as an object accelerates, its relative mass increases. To push an object with mass to exactly the speed of light would require an infinite amount of energy. It is mathematically impossible, but nature offers a bizarre loophole. If you travel at 99.9% the speed of light, you don't break the speed limit. You break time. This is the famous twin paradox. Imagine two identical synchronized atomic clocks. One stays on Earth, while the other boards a deep space relativistic ship. The ship accelerates to 99.9% the speed of light. To the observer on Earth, the spaceship appears to flatten, and the traveler's clock slows down to a crawl. But inside the ship, physics feels perfectly normal. The traveler's heart beats at a normal pace. Their coffee pours normally. Their clock ticks normally. To the traveler, they aren't moving through time slower. Instead, the physical universe itself mathematically shrinks in front of them. This is called length contraction. After half a year, the ship turns around and flies back to Earth. This turning point, the change in acceleration, is what permanently breaks the symmetry between the two clocks. When the ship returns, the traveler has experienced exactly 1 year. But due to the Lorentz factor at 99.9% light speed, they find that 22 years have passed on Earth. The traveler is now 21 years younger than their twin. This isn't an optical illusion, it is a literal biological time jump into the future. This creates a massive nightmare for any advanced civilization. An interstellar empire cannot exist as a unified entity. Time dilation fractures them permanently. If an emperor sends an urgent message to a colony just 500 light-years away, the emperor will be dead for centuries before the message even arrives. Each colonized star system would evolve its own culture, its own biology, and its own species, entirely cut off from the rest by the insurmountable walls of time. Physics ensures that the universe will always be a lonely, majestic archipelago. To travel the stars is to say goodbye to your own time forever. Everything we have discussed so far, stars, black holes, planets, and even ourselves, is made of ordinary, visible matter. But there is a massive illusion at play. All the luminous matter we can see through our telescopes makes up only 5% of the entire universe. The rest is completely invisible. In the 1970s, astronomer Vera Rubin observed spiral galaxies and noticed a major mathematical problem. The stars at the very outer edges were spinning far too fast. Based on the visible mass alone, gravity shouldn't be strong enough to hold them. These galaxies should gracefully scatter their stars into the empty void. But they don't, because they are encased in a massive, invisible sphere of extra gravity. We call this unseen structural glue dark matter. Dark matter outnumbers normal matter by 5 to 1. It doesn't interact with light, it doesn't emit heat, and it doesn't collide with physical objects. Theoretical physicists believe it might consist of WIMPs, weakly interacting massive particles. Right now, trillions of these ghost particles are passing straight through your body every second. Zoom out to the largest possible scale. Dark matter acts as the invisible skeleton of the universe. It forms an unimaginably vast structure called the cosmic web. The visible galaxies are just glowing dewdrops clinging to this dark spiderweb. They flow gracefully along these invisible rivers of gravity into massive clusters. But this grand architecture is currently caught in a silent, cosmic tug-of-war. While dark matter pulls the universe together, something else is pushing it apart. Enter dark energy. Making up a staggering 68% of the universe, it resides in the empty, dark voids, perfectly nestled between the web's filaments. This means 95% of our reality is made of two mysterious entities we cannot see, touch, or fully understand. The visible universe is just the foam on the ocean, and right now, dark energy is winning the war. It is stretching the cosmic web so fast that the dark matter skeleton is slowly, irreversibly stretching out of reach. We live in a fleeting era where we can still see the grand skeleton of creation, before the dark energy pushes it all permanently into the shadows. But before the universe fades, humanity has one final cosmic question to answer, and it lies hidden within the birth of the very first atoms. Of all the mysteries we've covered, from black holes to dark energy, there is one fundamental question that haunts physicists more than any other. Why is there something rather than nothing? Why does the universe exist at all? To understand this, we must look at the mathematical mirror of reality, antimatter. For every fundamental particle of matter, there is an exact opposite twin. An electron has a negative charge. Its antimatter twin, the positron, has a positive charge. If these two twins ever touch, they annihilate instantly, converting entirely into pure light. According to the standard model of physics, the Big Bang should have created exactly equal amounts of matter and antimatter. If that were true, in the first fraction of a second after creation, all the matter and antimatter would have collided. The entire universe would have annihilated itself instantly. We should be living in an empty, boring void, filled with nothing but harmless, drifting photons. No stars, no planets, no biology. But obviously we are here. The stars are here. Somehow regular matter won the war. This is known as the baryogenesis asymmetry. Physicists calculate that for every 1 billion antimatter particles created in the Big Bang, there were 1,000,000,001 matter particles. A tiny, almost imperceptible glitch. Every single star, every galaxy, every planet, and every living creature in the universe is made entirely from that tiny, leftover fraction of a percent. But why did this imbalance happen? What caused the math to break in favor of matter? No one knows. To solve this, humanity built the most complex machine in history, the Large Hadron Collider at CERN. A massive, freezing ring buried beneath Europe. By smashing protons together at 99.999% the speed of light, we recreate the exact conditions of the Big Bang, searching for the particle that broke the symmetry. Our very existence is a mathematical anomaly, a 1 in a billion cosmic typo that allowed a dead universe to blossom into life. Every atom in your body, every thought in your mind, and every star in the sky is the beautiful result of the universe making a mistake. We began this journey 45 minutes ago, looking for alien voices in the immense, silent dark of the cosmic ocean. From bioluminescent space leviathans swimming through asteroid belts, to advanced civilizations harvesting the rotational energy of black holes to outlive the end of time. But perhaps the most complex, highly advanced communication network in the entire known universe is the one currently sitting inside your own head. The human brain contains roughly 86 billion neurons, connected by over 100 trillion synapses, constantly firing to create consciousness. Astoundingly, this number closely matches the estimated 100 billion stars in the Milky Way. And when mapped visually, the resemblance is haunting. As the legendary astrophysicist Carl Sagan beautifully stated, "We are a way for the cosmos to know itself." The universe isn't just a dead machine of math and gravity. Through us, it has developed eyes, ears, and a voice. Every time we look through a telescope, decode a radio wave, or solve a quantum equation, the universe is literally reading its own source code. So, when we listen to the sky and hear only silence, we shouldn't despair. The silence isn't a graveyard. It is a blank canvas. If we can survive our own self-destructive tendencies and pass the great filter, we have an unimaginably grand destiny ahead of us. We are the Firstborns. We are the ones who will write the Xenolinguistic dictionaries. We are the ones who will build the cosmic networks. So the next time you step outside and look up at the night sky, don't feel small. Feel incredibly, unbelievably lucky, because you are a piece of the universe, and for a brief, beautiful moment, you have been given the gift to understand it. Thank you so much for exploring the cosmic ocean with us. Until next time, stay curious.